All right, so I've got a bit of a case of the hiccups here, so you'll have to excuse the random interruptions as we talk here about um, air movement and meteorology, at least in broad strokes. So the first thing, of course, is meteorology, study of atmospheric phenomenon. Meteo actually refers to things that are in the atmosphere. A meteor is technically anything that enters the atmosphere, right? Not to be confused with an asteroid in outer space. So meteorology, the study of atmospheric phenomena, uh, as it says, meteoros, high in the air. Um, and it can be made out of precipitation of some kind, right? So a hydrometeor might be a piece of hail or a snowflake. Lithometeor, lith, again, rock. So this is going to be something like dust or there's some kind of solid particle in there. Smoke and haze also fall into this usually. And then electrometeors, lightning, thunder is just the sound effect of lightning, of course. So that can be included kind of as an electrometeor. We're not going to talk too much about the different kinds of meteors here, but we will talk about the difference between weather and climate because this is extremely important. And as we talk about climate, we need to separate that from our perception, excuse me, hiccups again, of weather. So weather is a short-term variation, usually caused by the movement of air masses, right? So it is some kind of change in the atmosphere or the atmospheric phenomena of a region based on the movement of air around the Earth, whereas climate is kind of a long-term, there's that hiccup again, a long-term measurement. So this is a long-term average usually, and that can be, say, over an entire year. So we know that, Egypt is dry year-round, so we could call it dry. There are regions of sub-Saharan Africa that have rainy seasons, but they are still generally dry year-round. So on average, they are arid, or they have arid climate. But we can also talk about climate that's kind of averaged over what's called an ensemble average of kind of the month-to-month variation. So on average, the climate of Nashville is such that it is in the 90s. God, the hiccups in June and July, or at least July and August, and then in the 20s or so in December, right? That would be the climate for a given month. So it doesn't necessarily have to be a constant average across across multiple years straight. It can be the average of temperatures and precipitations in January, or the average in March for a particular region. And most of this video isn't going to be about climate, but I just wanted to introduce the idea there when we talk about weather, so that you can start thinking about it already. So we do know all about the unequal heating of Earth, and this is basically just going to cause certain regions to have generally cold air and certain regions to have generally warm air. Now we know that cold air is going to become more dense, it is going to sink, therefore, than warm air, which rises and is less dense, right? This movement, the up and down movement in Earth, right, is going to cause there to also be, if there's a lot of movement up at the equator, then that creates a vacuum beneath it, right? And so that will pull air from north to south in the northern hemisphere and south to north in the southern hemisphere, kind of just towards the equator. And since cold air is sinking, it's creating a high pressure area here where it's pushing down harder because it's trying to sink down towards the Earth, and it will push away from the poles. So there's going to be movement away from the poles, near the poles, and towards the equator, near the equator. I'm sorry about the hiccups, guys. And you would think in between there'd be a uniform flow, but actually that's not what we see. And I'll talk about that in a second when we talk about the Ferrel cells, like Will Ferrell, spelled the same, where there's actually a reversed flow there. But in general, the pole, the air is flowing away from the pole, and the equator, it's flowing towards the equator. When we have north-south movement of air, just like the up-down caused a north-south movement, the north-south movement of air is going to turn east and west because of the Coriolis effect, and I thought that was the next slide, but I guess not. So up and down movement is really the first thing that happens with air, and then that will cause secondary north-south movements and apparent east-west movements. So in general, when we talk about movements of air, they move as masses. Air mass has kind of like the same rough temperature and humidity, so it could be a mass of really humid air or a mass of really dry, cold air or something like that. So when we talk about, for example, those Arctic blasts that give us that like 12-degree day in November, you remember that? That would be a very cold air mass that moved over Nashville. And it came from the source region over which the air mass forms. You can guess what that is, the Arctic, right? The pole. And then basically we say that they are either polar or tropical, or maritime or continental. Obviously maritime, it's over the ocean, there's going to be a lot of evaporation, so it's going to be more humid. Continental, it's going to be over the continents, a lot less evaporation, so it's going to be more dry. And then polar and tropical, obviously tropical is warm, polar is cold. So continental polar would come down from here, maritime polar might come down from there. Continental tropical, here we would get that in central Mexico. We might see that in North Africa, right? Continental tropical air masses. And then maritime masses, again, are much more humid, even if they're cold. You can look at these. You should be able to reason these kinds of things out. You shouldn't need additional information. Though the one kind of exception is, well, that's continental Arctic instead of Arctic Arctic. Arctic air masses are sometimes separated. If they're continental Arctic, then they are basically the same as continental polar, right? Cold and dry. And if they are maritime Arctic, because the Arctic is an ocean, then they are more cold and moist. And they're a little drier than these maritime polar air masses, just because it's so cold that there's not a lot of, like the saturation for water is very low in the air. Continental Antarctic is what that CAA stands for. But, all of these should be pretty straightforward. E here is equatorial, so these are maritime equatorial, continental tropical. See, as I said, North Africa, we got that. Continental polar and continental Arctic here in Siberia. Maritime polar, maritime tropical, maritime equatorial. None of these should be very surprising at all if you see this. You should have been able to work these out all on your own. In other words, don't memorize anything like this. Just try to work it through. And as we said, the air masses move. Generally, this is because originally there was some air somewhere moving up or down, towards or away from the Earth, and then that causes a vacuum or a high pressure area, a vacuum down here, or high pressure area up here that will push the air either away from the pole or towards the equator. And then that's going to move a whole lot of other air surrounding it in what are called basically convection cells. Just like there are in the mantle, there are convection cells of air. And this is kind of what that would look like. If we've got a high temperature region here, that air is going to warm up and going to rise. create a vacuum, which draws air from afar, which at some point will create a vacuum where there's sinking, and we have this cycle here where this high pressure air is pushing this cold air down and back towards. So these are the convection cells if we did not have a rotating Earth, right? It would go straight from the pole all the way down to the equator where it's rising. This makes total sense, right? This is hot air, it's rising, cold air, it's sinking. So this seems like what we would have, but this is actually not the case because of the rotation of Earth. If Earth were a totally still marble in outer space, we would have this, but because it's spinning, air that is over the Earth and not kind of riding along with the spin, obviously is going to be deflected. So if we imagine this was like a sheath of air outside this marble that's the Earth that's not rotating, it would move like this. But then if we started moving the Earth underneath it, started rotating it other direction, this side to this side. So it's rotating like this. Then the apparent movement gets deflected, and we've already talked about the Coriolis effect a bit, but I encourage you to look over it again, maybe look up some animations or something online. I'm sure there's plenty of those on YouTube that would be very enlightening. So the air gets deflected to the side, and this creates a much more complicated wind system where in the poles we have things moving away from the pole, but also spinning kind of in this direction as the Earth, you know what, I said it wrong when I said which way the Earth rotates. I am just crazy. Sun rises in the east, which means the Earth is rotating this way, right? So if the Earth is rotating this way, then the air that is kind of just staying still above the Earth appears to move this way, right? But this cell here in the middle kind of compensates for all that by reversing. And you don't need to understand the exact physics, of course, of how these happen, but just appreciate that at the poles they are called easterlies because they move from east to west. Same with kind of in the tropics, and up here in temperate regions, they are westerlies moving west to east. That's why our weather kind of comes through Nashville in this direction here and not the opposite. And why our weather always shows up where my parents live in North Carolina a few days later. I also will need you to understand, or not understand, but know the names of, so that if I use it on a test, you know, you can reply correctly. This is the polar cells, and they move again away from the pole on the surface and towards the pole higher up. This is called the ferrule cell. It's not listed here, but it is. And the ferrule cell is moving north on the surface and then south again up high. And the Hadley cells are these equatorial cells where there's this convergence at the equator where there's a rising, and then the air, as it slowly cools down, sinks at about 30 degrees latitude. And conveniently, these are separating the planet into about equal, not equal areas, but equal latitudes, right? So the top 30 degrees of latitude and the bottom 30 degrees of latitude here are the polar cells, and then the polar cells are not even visible here. Or the Antarctic cells not even visible here, but the ferrule cells are from 30 to 60 degrees latitudes, and 0 to 30 degrees latitudes are the Hadley cells. I want you to appreciate at least the name ITCZ for the intertropical convergence zone. Again, that's basically where this tropical cell and this tropical cell meet. They're therefore intertropical, right, between the tropics. Convergence zone, so it's where this air and this air converges and pushes up. Because of that, the wind, if you wanted to say which direction the wind was blowing here, the best answer would be straight up. So if you were a sailor back in ye olden days, and you passed through the ITCZ, or the Intertropical Convergence Zone, the wind would not be blowing your ship very fast, right? Because the wind is blowing effectively straight up, and it might go one way or the other, which is why they're called trade winds, just because the wind isn't very strong there. And sailors referred to that in the olden days as the doldrums. So those were around 0 degrees latitude around the equator, where basically the wind stopped and you had to kind of be lucky to get out of it. It was a dangerous place to cross in the age of sail. Another result here are the jet streams, and they are kind of involved in the formation of these westerly winds, right? Or meaning going from west to east. And the jet streams move in that direction with those cells. Generally right at the boundary between the different cells here. So this would be the Ferrel cell, polar cell, Hadley cell. Don't worry too much about the jet streams, just appreciate that they are kind of at the boundaries of the cells and they move in the direction of the westerlies, west to east. This is just talking about how they are at kind of the boundaries of air masses and the boundaries of different flow areas. The next thing I do want to talk about in detail, and you guys should understand, are the different kinds of fronts. You see these symbols on the weather reports, talking about cold fronts, warm fronts. You've probably heard about those, talking about when it's going to become warmer soon. They'll say, oh, there's a warm front, or when it's going to become colder soon, oh, there's a cold front. There are also occluded fronts and stationary fronts that I'm going to expect you to understand also. So the front is the boundary, or this says the collision between two air masses of different densities. So a cold air mass and a warm air mass. The boundary between those is the front. So if you're in a war and you're at the front, right, it's the boundary between the two camps, right? So that's how what a front is in weather also. It's the boundary between the two air masses. So if we have a cold front, that means there's cold air that's doing the active movement. It's pushing warm air away. So the warm air, because that's more has more heat, probably more moisture, and it's also less dense, it will basically kind of push above or be pushed upwards by the cold air as the cold front moves in. And when you have humid air rising up and basically cooling down as it does so, it's going to condense, and there's going to be a lot of cloud formation. Whenever there's clouds, there can be precipitation. So this cold front often will create rainstorms of different kinds, and you need to be able to appreciate how that happens for any kind of assessment. Again, cold air comes in, warm air is pushed upwards, that cools it down, and it therefore will condense the humidity in this warm air. Warm front, oh, look at that compression. That is ugly. A warm front is basically the opposite, where the warm air is pushing in and kind of encroaching on the cold air. And because of this, it's going to push up, and there is going to be a little bit of lifting of the warm air, but substantially less than in the cold front, where it's just kind of like forcing the warm air up. And because of that, there will be cloud development and some precipitation sometimes, but generally this is less intense precipitation than the cold front. Right? So this might be a storm, whereas this might be a shower. It also means that there's going to be warm after this in a given place. So if we're here on the surface and this warm front pushes past us, we are now in the warm air mass instead of the cold air mass, whereas the cold front, it's cold afterwards. An occluded front is basically where you have three air masses. There's two cold air masses and one warm air mass kind of trapped in the middle, like a pincer attack here, right? So the advancing cold air pushes into this other receding cold air, and as a result, the warm air trapped in the middle in this pincer attack is forced upwards very quickly. And this is going to have a very strong storm just because it is pushed up very far, very fast. So this is going to be kind of your most severe weather. Occluded front, then cold front, then warm front. And the last one is a stationary front. And here you've got a cold air mass and a warm air mass that are kind of kissing, but they're not actually pushing against each other for whatever reason. And because of that, there's not going to be very much lifting of the warm air or very much condensation of the humidity in that warm air. So even though this shows kind of showers, there's not really usually going to be much precipitation. This is going to be a pretty calm environment, even though on one side of town it might be cold and on the other side of town it might be warm. Town is an exaggeration. Of course, these are like the size of continents. So one side of, say, a state and the other side of a state would be more accurate. But this is, again, not going to have a lot of lifting of warm air, and so therefore not going to have a lot of precipitation. Remember, lifting of warm air with the moisture in it is going to be what causes precipitation, because there's going to be condensation in the form of clouds. I would read about pressure systems. The basic idea is just rising and falling air again. And does this link work? Let's see. Video unavailable. Nope. So if you can find the ultimate guide to extreme weather, there are a couple of them with the same name. One of them is really just a video of tornadoes, which is kind of entertaining. Anyway, have a look up or a look at it. I trust that you all are doing your own independent research also, as well as looking in the book. But the slideshow at least should help you focus on what is kind of the most important from all this material. All right, thank you, guys, and I will look forward to good discussions over the weekend.